In this video, we're going to introduce the concept of melting and crystallization in a binary eutectic, where in this case we have diopside and anorthite, which have no solid solution between these two. So no molecules of anorthite will dissolve into the diopside crystalline structure, and no diopside dissolves into anorthite. So they're completely separate minerals, and we get this eutectic geometry, these phase boundaries as we see here. So let's say we have this setup here where we have diopside and anorthite, and we have twice the amount of diopside as we do anorthite. That's the way I've tried to draw this. So that means 2/3 of the system is diopside. So the diopside is about 67 weight percent, and anorthite would be about 33 weight percent. So that would put the system over here, about 33 weight percent silica, or 33 weight percent anorthite. So what would that mean in terms of melting? Well, we would take that bulk composition, follow it upwards to 1274, and there the temperature would sit at constant temperature while we begin melting. But what happens with melting? Well, the first melt we would get would be here at the eutectic composition. And let's say this green box represents that eutectic melt. That melt will form at the grain boundaries. So wherever the two minerals are in contact, that's where the first melt will form. The melt will not form in the interior of diopside. Why not? Diopside itself melts at diopside itself melts at 1392, and anorthite over here melts at 1553. But this melt here at the grain boundaries, you could think of it as kind of a grain boundary instability. These grain boundaries, when they're in contact with one another, form kind of a mechanical instability where the material can melt at a much lower temperature, 1274, well below the melting temperatures of either one of the two pure minerals. Now, with this composition that is mostly diopside over here, as we follow the bulk composition upwards, we would eventually hit the diopside plus liquid field. The only way we could do that is by melting out anorthite first. So as we increase the heat, the temperature will stay fixed. That's kind of a tricky part. But as we increase the heat, the melt will grow. It'll grow into the diopside field and the anorthite field both, but it'll eat away at anorthite at a faster rate than it'll eat away at the diopside. And eventually, we'll have some certain amount of melt. And so here's our liquid field in the light green here, and then we'll just be left with diopside by itself. And once we do that, then any further melting will just eat further away into the diopside crystal. So the liquid starts here at the eutectic composition, and as it eats away at diopside and anorthite, its composition remains constant. So if we come back to that somewhat initial state over here, this liquid is going to eat equally into diopside and anorthite at such a rate that the composition isn't fixed. But once all the anorthite is gone, so it's eaten into anorthite and it's eaten into diopside, the only thing it can do now is eat up more diopside, the little bit of diopside that's left over, and so that means it'll leave the eutectic composition, and the liquid will become more and more enriched in diopside until it hits that bulk composition, which we put over here at 33%. And when we finally hit that composition where the liquid is equal to the bulk composition, that would be about there, then the bulk composition will simply get hotter. We'll have a liquid, everything will be molten, and the system will simply be higher in temperature. Let's take a look at the crystallization case. What if we have something that is entirely liquid, and again at about 33 weight percent anorthite? The system would cool until it hits a temperature of about, looks like about 1330 degrees centigrade or so. That's when the first little bit of diopside would appear. So we have a little bit of that dark green diopside that appears as crystals. As we pull diopside components out of the liquid, then the liquid would become more and more rich in anorthites. The liquid would follow this curve downwards until it finally hits the eutectic composition. And then when it hits the eutectic composition, that's when the first little bit of anorthite would appear, and then anorthite and diopside would crystallize together, eating away at the liquid, and we'll try to have this happening as equally as possible. There's probably cleverer ways to illustrate this, but there's our liquid just getting smaller and smaller, anorthite eating in this direction, diopside eating away at this direction. We're forming both the minerals in the same proportions, in eutectic proportions, until all the liquid is gone and all we have is diopside plus anorthite that's back at the original bulk composition at 33%. So that gives a little bit of physical intuition as to what is happening in a eutectic system. Diopside and anorthite don't mutually dissolve each other's components into one another. So they have this kind of so-called eutectic reaction system, excuse me, not a reaction system, but a eutectic relationship whereby they precipitate together and the melting is really driven by instabilities on those grain boundaries, and they precipitate and melt together at eutectic proportions when both minerals are present.